Hi, I am presenting learning attention propagation for compositional zero-shot learning. I am Gul Zain, and this project was conducted in AV department under supervision of Dr. Zeshan Afzal and in collaboration with ETH Zurich. Compositional zero-shot learning is the task of classifying samples by compositional labels. Compositional labels consist of object and state. States can also be referred as attributes. During training, we see all states and objects but not the compositions, and at test time we have to predict on novel compositions. For example, we will see old bridge, but during test time we'll also have to predict old car. Some approaches have tried to disentangle states and objects. If we can disentangle states and objects, we can predict their novel compositions. However, these approaches lag behind on real-world datasets. Some other approaches, such as CGE by Naeem et al., uses GCN to exploit dependency between compositions that share state or object in order to propagate knowledge between them. We argue that real-world images contain more than one valid composition. For example, this image label is old car, but we can also see a tall tree and a tall building. We use self-attention based transformer to exploit hidden interdependency structure between compositions to propagate knowledge between them. We call this Cape Propagator that learns to embed compositions in shared semantic space. Our method figure is provided here. We first create tensor containing compositions. Then we apply self-attention followed by residual addition into the input compositional tensor. This tensor is then projected into the shared semantic space. We use cross-entropy loss as an objective function. Compatibility score is calculated as cosine similarity between image and projected embedding. Propagation routes are learned through the Curie key self-attention mechanism. We show results for MIT States dataset. We outperform in AUC and are comparable in unseen and seen accuracies. We outperform in all metrics amongst the networks with frozen backbone. Now we show results for CGQA dataset. We outperform in AUC, harmonic mean, and unseen accuracies. Amongst networks with frozen backbone, we outperform in all metrics. Here we show qualitative results. It can be seen that our model shows good performance in complex compositions like blue table. Amongst suboptimal results, we observe that our model is able to predict correct compositions in top 3 predictions, such as dented armor, deflated rubber, and gold mirror. We also observe that in incorrect predictions, our model is producing meaningful predictions, such as large zebra image has tall grass and also a zebra that is standing. Here we show top 5 and bottom 5 activations for each composition query taken from the heads of multi-head attention. We observe that these activations are meaningful, such as weathered redwood is related with broken log. Weathered redwood may contain broken logs. Furthermore, red floor is related with carpeted floor, wherein red floor can have a carpet as well. Here we show images of some of the compositions from previous slides. We can see that red floor have carpet in it and weathered redwood have broken logs in it. Thank you for your attention.